we had covered the light emitting diode and photovoltaic cell. So I thought that why not discuss fiber optics. I happened to be in Delhi for a month, and one of the very important instruments which was used in diagnosis was basically something based on fiber optics, and I really began appreciating even more how important this particular area is. So let me tell you about fiber optics in today's lecture. Now, just so that you get a understanding, of what kind of things have been done with fiber optics. This was around 2016. I think that Google laid a undersea cable connecting the US and Japan, and just imagine 9,000 kilometers of optical fiber. I mean, it's just mind-boggling, under the ocean, and it was going to have something like a 60 terabyte per second capacity, information transport capacity, So it just gives you a feel, for what's really going on and how important it is. Okay. Now, if you also, it's a great lesson in really material science and also the very novel ways in which people solve problems. Okay. Like for example, these are the fibers, which we'll be discussing today. They're the optical fibers. And then you look at the number of layers of protection which are put over it, okay? Starting from polyethylene to mylar tape to stranded steel wires, aluminum water barrier, polycarbonate, copper aluminum tube, petroleum jelly, optical fibers. It's quite remarkable, and this is also another very interesting thing, that if you take a optical fiber, it's of course glass and it's very brittle. It'll break. But this is a very interesting area of composites. Where something which is brittle, okay, you can prevent it from breaking by making a composite with something which is very flexible. Like these cables, okay, and that's how they actually don't break. It's quite interesting. You can also try it out. Sometimes you take things which are brittle and put it maybe along with some rubber sheet. You can prevent it from breaking. Okay? So it's quite an interesting area of composite. Now, in fact, what I thought is in 2016-17, that batch, when I was giving this lecture to the people who had taken the course at that time, and very interesting that one of the students had asked me that why are we doing all this, and why don't we really look at internet through satellites? I dug out the lecture. Okay. Let's start from here. It doesn't matter.
So today, for example, there is a huge concern that with all this investment, would satellite communication completely disrupt everything? Right. Is it possible that would be a much cheaper option than laying these cables? And the view is that satellite communication cannot be as efficient in data transfer as this. But there are many other areas where this cannot do what satellite communication does. Like GPS is a great example of you have to do it by satellite communication. So they are complementary.
And look, I mean, we were having this lecture in 2016, and that's the time when this cable was put, and really there was no internet as such through satellites. But then, very, very disruptive technologies like these Tesla, Starlink, where something like 60 satellites were launched at one go, into space. Yeah? And now, in fact, with all this war raging in Ukraine, Tesla has offered that as a means of communication and to keep the internet, etc., going in Ukraine. I mean, this really would be a very, very disruptive technology, which might make fiber optics. I wouldn't say it wouldn't make it totally irrelevant, but it could reduce its importance in certain segments. But then there will be also areas where fiber optics will still remain very, very important, and doesn't matter what. And medical applications is one of those that I have in mind. Okay. But let me show you again what is vision. It's not very different like 50 years when Haber, for his Nobel lecture, he talks about what the situation would be in 1950 with there not being any nitrogenous fertilizer available, and how important it is that an artificial means of synthesizing nitrogenous fertilizer be developed. And so amazing ability to think way ahead, 50, 70 years ahead. Same thing is true about nuclear fusion, where people are looking at maybe 75 to 100 years ahead. And many of us, we struggle to think about what we'll do day after tomorrow. And so there's a world of difference in terms of vision. So this is another example where at the time that these patents were taken in the early 70s, and if you look at even prior to that, maybe in the 50s and 60s, when communication was much less demanding. I mean, you didn't have something like you're downloading a movie and it barely takes a few minutes to download it. I mean, you can imagine the kind of speed and volume with which information is being transmitted today. So it's very different. But these people had all anticipated long ago. Long ago means, I mean, in the 50s and 60s, they were already looking at what will be the situation in 2020. And that's the kind of thing that they were able to do. And really, I mean, vision, let me tell you, is one of the most important components of innovation. Yeah? Those people who can think way ahead of others are likely to be the winners, and they will have enough time to develop their technologies. Okay, I've seen a lot of companies very fashionable to say, "Hey, I want this day before yesterday." Okay, and it's they're bragging about how they kind of craft the whip and make people work and want things done yesterday. But the people who talk like that are people who were unimaginative, who could not actually think ahead of time. Okay? And that's why they have to do it day before yesterday. Okay? Not if you had thought 50 years earlier about what you need to do. Okay? So don't get carried away by very of this things which look like very impressive. To me, it's a sign of folly. And in fact, I'll give you another example. I remember when 1985, we had come to stay in Vashi. I had taken up a job, and there was nothing there. There were one or two buses that used to fly in the not even BEST or any of those, some other things. Auto rickshaws would charge return fare to bring you back or to take you somewhere. And around that time, 1986, I remember a huge bus terminus coming up. And I remember we would really laugh at why are they making all this? Such a huge bus terminus with 20, 30 different bus stands for different buses, etc. And you make a joke of it, but it is they who were visionary and we who were stupid, not being able to anticipate what is growth. Okay? And I was just admiring these people who do city planning and urban planning and their ability to think so far ahead. Okay? They knew it's going to fill up, and today that same place looks so congested, and you wish that it was 3 times the size. You know? That's the kind of thing that I mean by vision. So let us look at in this patent of Corning what they're trying to say. Now it's also very interesting. Corning as a company was really a company associated with plates and all these crockery and stuff like that. You know, that's what their main job was. Corning glassware, very famous. Then they of course moved over to ceramic type of glassware, you know, semi-ceramic things. But I'm sure at some point, you know, Corning would have said, hey, optical fibers, you know, are all about glass. And that's my core competency. Okay, I know how to process glass. So maybe I should get interested in optical fibers. I'm sure that that's the kind of decision their management would have taken, maybe in the late 50s or in the 60s sometimes. Okay. So again, I hope you can see, because if you are a company who are basically making cups and saucers, you may not associate yourself with optical fiber. Okay? But if you look at yourself as somebody who is competent in a technology platform, and for them it was processing of glass, then you might say, yes, I can. Why not? I mean, anything where there is glass involved, let me be in it. That's the way you will think. Okay. So this is from their patent. Okay. The increase in the amount of traffic that communication systems are required to handle has forced the development of high capacity systems. The presently used systems, which operate between 10 to the power 4 Hz and 10 to the power 8 Hz, although relatively new, have already become saturated in some frequency bands due to excessive traffic. To allow for needed increases in traffic, which the present systems cannot accommodate, commercial communication groups are presently installing high capacity systems that operate between 10 to the power 9 Hz and 10 to the power 12 Hz. Okay? And I'm talking about late 60s, you know, that was the state of art. Okay? Even with the increased capacity that these new systems will offer, traffic growth is so rapid that saturation of such systems is anticipated in the very near future. Therefore, to accommodate even more traffic, higher capacity communication systems operating around 10 to the power 15 Hz are needed. These systems will hereinafter be referred to as optical communication systems, since 10 to the power 15 Hz is within the frequency system of light. And you can see that that's true. You know, if you take nu is equal to c upon lambda, you put in the speed of light, and you let's say suppose you take a 400 nanometer wavelength, you can see that you're talking about around 10 to the power 15 hertz. You know, and so I mean that's visible light. Okay, we are talking about. Okay, so then it says waveguides are desirable for effective transmission of information by systems operating at frequencies above 10 to the power 9 hertz. Okay, and what is a waveguide? A waveguide is really a structure that guides waves. It could be electromagnetic waves or it could be sound waves with minimal loss of energy by restricting the transmission of energy to one direction. So it basically helps you to transmit in one direction, and it prevents the dissipation of energy in all other directions. You know, so it is really that which requires a waveguide. and it becomes even more important at these kinds of frequencies. Systems operating at frequencies between 10 to the power 9 hertz and 10 to the power 12 hertz normally use electrical conductive waveguides as a transmitting medium. So those typically you'll have some metal pipes, and the signals are really transmitted. The electric waveguides are just that. So that's what is used to transmit information through such things. Okay, but those are not satisfactory when you go to something like 10 to the power 15 hertz, and so that's where you require an optical waveguide. Okay, and that's really what the fiber optic is. So you can see how important this area of fiber optics is. And let me also tell you that in future, suppose let's say one day, I don't know, I mean, but if communication were to happen at even higher frequencies, maybe in the deep ultraviolet, then you may actually have to rewrite and redo some of the work for waveguides in that kind of region. Or maybe communication could even happen through X-rays, I don't know, because they're very short wavelength, very high frequency. So you never know. Okay, so but today it is optical waveguides which are important. Okay, now so let us. I'm not going to go into the physics of these things. Okay, for two reasons. I think that is outside of the scope of this course, which is more focused on innovation, and also because I myself I don't feel competent enough to explain it well enough to you. Okay, but those of you who are interested might want to go and read it up, okay, and try to understand better, okay, that what some of these things are really all about. Okay, but let me just briefly tell you that there are three kinds of light wave guides. Okay, one is what is known as the single mode step index fiber. Now, firstly, let me tell you that basically mode is these are the different ways in which you can pass information through these kinds of waveguides. Okay, and so each of them represents a mode. Okay, and these modes are orthogonal to each other. Okay, so they don't interfere with each other. I mean, those are the solutions of the wave equation, and so all the signals are additive. They add up from the beginning till the end, and they do not cause any destructive interference or constructive, simply because these are the orthogonal solutions. Okay, so that's important to know. Like in a single waveguide, actually the ray is really traveling absolutely in a straight line from beginning to end, whereas if I've got something like a multi-mode waveguide, I could be having several of these waves, okay, which are traveling together, through these fibers, okay. And then there is also something known as a multi-mode graded index fiber. Don't worry about all of these details, but it's important to know that when we are talking about this 100 Mbps kind of speed, or 8 Mbps, which people talk about, that all of these things really depend on what is the kind of mode that you use. Okay, and you can have, for example, a lower bandwidth. Okay, like in this particular case with a step index multi-mode, and bandwidth is really the volume of information that you are transmitting per second, or you could have a higher bandwidth. so lower or higher bandwidth, okay. And of course, there are compromises, that you make in these systems. There will be something which are better, something which are worse, okay. So that's what is important. As far as the single mode is concerned, the whatever I showed you, this Google laying a cable, those would surely be single mode, because that is what is used for long distance transmission over thousands of kilometers, okay. And whereas some of these other things could be things which you are transmitting over maybe a kilometer to 10 kilometers, those kinds of things. Or if it is in your body, you're only talking about a couple of meters, right? That the information or the signal has to be transmitted. Okay? Now, the other thing is, because it's an optical communication, the other very, very important thing which was invented was really these lasers, and the type of laser which has been used are these diode lasers, okay, and they've got a fairly long wavelength. It would be close to about the near infrared region. This was actually invented by the Russians, and so it's a two-component thing. I mean, you need a fiber and you need a suitable light source, okay, which is very, very coherent, okay, and that's what a laser light source is. It's extremely coherent. Okay? So that's very important. Now, as far as today's innovation is concerned, what I'll be focusing on are there are just two important parameters for you to note. One is that you will see that this is one inner pipe or a rod, this one, and this is an outer one, okay. And so this is like the rod, and this is the cladding. Okay? And so that's important. You can see that, for example, here, the inner diameter is much, much less. And so you're having a very high ratio between the radius of the cladding and the rod. Whereas here, the rod would be the thing which is really the larger diameter. Okay, so that's very important. Okay, now who actually taught all these things of what exactly you have to do for these different kinds of transmission? Now, it does. Would I imagine Corning to be knowing all this? Possibly not, because if you are a company making cups and saucers, that you will delve deep into physics and have physicists on your payroll is unlikely. But then you can always go and talk to others and take the help of others who might be experts. And you can say, we are into glass and we think that we would be interested in optical fibers, but we don't know ABC about it. Okay. And someone says, no problem. Yeah, you go to this university, talk to Professor so and so. That person is an expert in this, and that's how they probably interact and do things. Okay. So in the patent, what they write is, the conditions under which propagation of a particular mode will no longer be localized within the core of an optical fiber can be expressed in terms of a cutoff value U. An exceptionally complex equation and an explanation thereof, from which the value of U for a particular mode can be determined, may be found on page 55 of Fibre-optics, Principles and Applications by N.S. Kapany. I'll tell you a little bit about him. He passed away a few years ago and received the Padma Vibhushan last year. Okay, and so I'll tell you a little bit about him. On the same page of this book, Kapany expresses a fiber characteristic term R in terms of the optical fiber variables by the equation R is equal to 2 pi A upon lambda square root of n1 squared minus n2 squared. So what are these? Okay, so A is the diameter of your core. Okay, that is what A is. Okay, and what are n1 and n2? N1 and N2. N1 is the refractive index of the core, this part. Okay, and N2 is the refractive index of the cladding. Okay? That's the equation. That's all you need to know. And of course, if you write it in this form, okay, you can figure out that obviously N1 has to be larger than N2. Otherwise, you will get an imaginary number, a complex number. Okay. So, so we know that the refractive index of the core must be higher than the refractive index of the cladding. Okay? And also there is a relationship which will become evident between what will be the requirements or in terms of N1 minus N2 and A, which is the core diameter, okay, to be able to have the value of R, which is lower than the cutoff value U. Okay? So that's what it is, and all of you, so I won't spend any time on that. And as a company, that's all that Corning needed to know. Therefore, what do I have to do? Just tell me. Well, we don't understand all these other things. I don't want to know about all the principles and all, but just tell me, okay, what do I have to do? Okay, now who is this Kapany? Okay. He is Narendra Kapany. Okay. Died about 3 years back, and since 2015, when I was when I've been teaching this, and I found out about Narendra Kapany, and I used to ask people, have you ever heard about Kapany? I used to even ask physicists, and they say, no, we've never heard about him. Okay, and he is the man who is the originator of fiber optics. Okay, he and his professor, I presume it's his professor, Dr. Hopkins, at Imperial College in London. Imperial College is one of those great institutions, the home of zeolites. They made the first synthetic zeolites in Imperial College. Fiber optics is theirs. And about 2 years back, when the COVID problem started, the first modeling prediction of how these things will spread was actually done by the Imperial College. So quite a remarkable place. And I just thought I'll read out. There was an interview with Narendra Kapany, and which I read, and so I'll just read out, because I think it is quite interesting to see what got him interested. So many scientists conceived of bent quartz rods carrying light and even patented some of these inventions. But it took a long time for these ideas to be converted into commercially viable products. One of the main hurdles was the considerable absorption of light inside glass rods. In other words, you want an ideal total internal reflection or a single mode where the light just passes through. Narendra Singh Kapany recounted to the author, when I was a high school student at Dehradun, in the beautiful foothills of the Himalayas, it occurred to me that light need not travel in a straight line, that it could be bent. I carried, of course, we know that you can bend light if, for example, it is moving from some location with one refractive index to another. We know that you can see the bending of light. Okay, but he actually was going all over the place. He even wanted to know if light can just go in circles. And so it was interesting. As a school student or as a college student, that was something that interested him. And he went to study after that in Imperial College to do his PhD. Okay, and probably told his professor about his interest. when I actually it was not an idea but the statement of a problem. When I worked in the ordnance factory in Dehradun after my graduation, I tried using right angle prisms to bend light. However, when I went to London to study at the Imperial College and started working on my thesis, my advisor, Dr. Hopkins, suggested that I try glass cylinders instead of prisms. Just look at it. And so Hopkins said, all this work has always been on plane surfaces. Why don't you look at curved surfaces? And see what happens with curved surfaces. Okay? So I thought of a bundle of thin glass fibers which could be bent easily. Initially, my primary interest was to use them in medical instruments for looking inside the human body. Now, I hope you can see what extraordinary creativity. And we are talking about the early 50s when nothing like this existed. The only thing that people could do at that time was really do X-rays. But those were all for hard tissues like your bones and things like that. But if you have soft tissues, where there was no way of looking inside your body and actually seeing what's happening to them. Later on, of course, sonography and many other things, MRI, this, that came out. But in those days, there was nothing else other than X-ray. Okay? But look at where his interest was. His interest was in looking inside the body. The broad potential of optic fibers did not dawn on me till 1955. He had no idea about communication, the area of communication, and that will become the dominant application of fiber optics. It wasn't, he didn't think about it at that time. And he says that it was then I coined the term fiber optics, So he is the man who coined the term fiber optics. And he, and I presume his professor, wrote all those equations which I showed you. They worked out all these things. Okay? And probably it just remained as a treatise. And now, this is another thing about places like England, especially England, because I've had this good fortune of when I was looking after the strategic research in ICI, and I would go and meet so many professors from various parts of the country, even in France or in the US, and go and talk to them about various things. Okay, and always you'll find someone who is quite knowledgeable. Second, you'll always find an industry or somebody who has curious people and say, yeah, I'll help you, and that's the reason why they are. Whereas you go to our places, I mean, they cannot see beyond their noses. If you talk about something like this, they'll just ask you to get lost. They'll smile at you, but nothing more than that. Kapany and others were trying to use a glass fiber as a light pipe, or technically speaking, a dielectric waveguide. But drawing a fiber of optical quality, free from impurities, was not an easy job. That was not something that Kapany wanted to bend light, but he had no idea about how to process glass. But what did he do? He went to the Pilkington Glass Company, which was the biggest glass company, and Pilkington, as you know, are the inventors of float glass, which is all the glass that we use, all our windows and everything, the flat glass is all float glass. Okay, so Kapany went there and they manufactured glass fibers for non-optical. They already were manufacturing glass fiber for non-optical purposes, maybe for some other applications. Okay, so Kapany, got hold of these things and developed his treatise. Okay, now it's very interesting that Kapany, like for example J.C. Bose, did not get the Nobel Prize. I thought that why Kapany? I thought both Kapany and Hopkins should have got it, because theirs is the first paper. Okay? published in Nature around 1955. Okay, they coined the term fiber optic. Okay, and they developed all the equations. Okay, for this, but as he very correctly says, that he did not really think about the role of fiber optics in communication, and maybe that's why they didn't give it to him. But I sometimes find these things so unfair, that the real originators of ideas, the greatest of minds, have not been given it. So, I mean, keep this in mind and develop a respect for many of the people who never got a Nobel Prize, okay? But in my view, they were far greater. Okay, now, why did I switch to the lecture to today? Well, there were two reasons. One was that, I saw a synergy between this invention of fiber optic and the work of Chapin on solar cells. I'll ask you, what exactly do you think I have in mind in terms of the overlap between the two? Okay, and the second was I'd gone to Delhi because my brother had developed colon cancer, and so he had to undergo two endoscopy, and in one of them, they actually managed to remove some polyps from the descending colon, the large intestine, the descending part of it, and because of that, subsequently they removed only the ascending colon and a part of the transverse colon, and that has saved him a bit, because otherwise the quality of his life would have deteriorated quite substantially. So I mean, I realized what an important equipment that is, and not only to peer inside the colon, okay, and identify, okay, where exactly the tumors are, or the growth is, but even to actually use it for surgery. Okay? And in fact, the person who removed those polyps is a Padma Shri for his work on gastroenterology, very famous man. Okay, and so I was just really just amazed, and I was thinking about Narendra Kapany and his great vision, in the 50s, and we are talking about, today it's so commonplace. Okay, these endoscopes, and where you can look at the entire digestive tract, and pinpoint things. Okay, and so let us. But then, as I told you, the focus with which I'm going to give you or talk to you is really the focus related to optical communication, because that is, as I said, in terms of volume, there is no comparison, between that and medical applications. Although medical application is very important, but in terms of volume, naturally, it's the communication which is much bigger. So let us try and quickly go through this. In the early 1969s, signal loss in glass fiber was 1 decimal per meter. As you would have seen, a waveguide, it was used both for electromagnetic waves as well as for sound waves. Okay, and it was ever since the days of the telephone. It is sound waves. People were always using it for telephone, right? To talk to one another. So the sound waves and the decibel, the signal intensity was important. Okay, and that terminology has remained. So even when they're talking about optical fibers, they still talk about in terms of decibel. So in the early 1969s, okay, signal loss in glass fiber was 1 decibel per meter, which meant that after traversing 10 meters of the fiber, the signal was reduced to 1/10 of its original strength. Okay? After 20 meters, the signal was a mere 100 of its original strength. Okay? As you can imagine, after traversing a kilometer, no perceptible signal was left, and therefore it was not a suitable waveguide, where a waveguide really should be transmitting in one direction, but these were obviously having losses in all directions, even in the transverse directions. Okay, a small team at the Standard Telecommunications Laboratories in the UK was not put off by this drawback. This group was headed by Corboviak and later by young Shanghai-born engineer Charles Cow. Cow studied the problem carefully and worked out a proposal for long-distance communications through glass fibers. He presented a paper at a London meeting of the Institution of Electrical Engineers in '66, okay, pointing out that the optical fiber of those days had an information carrying capacity of 1 gigahertz or an equivalent of 200 TV channels or more than 200,000 telephone channels. Okay, but then what he says is that whatever they had, there was a loss of something like 1,000 decibels per kilometer. So it was not practical. And so Cow said, but I can take a bet, that over a period of time, people will be able to reduce the signal loss to something like 20 decibels per 10 to 20 per kilometer. Okay. And he said that if this can be done, there would be a revolution in transmission. And look, I mean, way ahead. So you need not be hesitant to dream. Forget about whether it exists today or not. Nothing prevents you from saying, if it happens, then this will be a great thing. What prevents us from doing that? Nothing. So and then look, as I told you, especially in UK, they have these people. It is the British Post, and mind you, British Post, they were at that time in the letter business, but they recognized that if communication happens in this way, maybe people will not write letters. Things will get transmitted through other means. That's exactly what has happened. All this email, everything, whatever we talk about, okay, it's competed and kind of outcompeted letters. So all this normal post was has gone, and British Post transformed itself into British Telecom, okay, and recognizing that it's going to be very, very important. Okay, but it was really Corning who were able to make, as I told you, this the optical fiber of unbelievable quality, and at the same time, both in the Bell Labs, your Russell Hole, that was one of the links that I wanted to point out, and also in Leningrad, this institute, they made the first semiconductor lasers, which were required to basically be used as the light source. Okay, and so the two together is what heralded this massive revolution in communication. Okay, now, and also to tell you, in fact, it's interesting. It says that today's fibers are so transparent that if the Pacific Ocean, which is several kilometers deep, were to be made of this glass, we could see the ocean bottom. Imagine that, and I mean, that's the level of clarity of these glass, which is used, that they were able to achieve. Okay, now, as we discussed already, this equation, okay, I'm not going to read out the full details, okay, but what they basically said is that, suppose, let's say that if I only take the single mode, okay, this mode, the single mode, okay, and they worked out that it will have to have an R value which is less than 2.405. Okay? Now, when they put that R value as that, okay, they were able to derive the relationship between N1 minus N2 and A. Okay? And what they said is that, look, if my A has got to be very, very small, Or if my N1 minus N2 has got to be large because I cannot control refractive index in in such a narrow range. So whatever range they contemplated, then they said, well, if you want to do that, then your inner diameter, the core, will be extremely thin. Okay, and so they were able to get some idea, quick idea of numbers. So if R is set equal to 2.405 and equation 2 is evaluated, it can be seen that a method of limiting light propagation of a desired wavelength to one mode is to coordinate the parameters A, N1 and N2 of the waveguide. That is, if the difference between the two indices of refraction N1 minus N2 increases, the core radius A must decrease, and if N1 minus N2 decreases, the core radius A must increase. Producing waveguides having core and cladding indices of refraction within limits necessary to maintain single mode propagation is difficult even for waveguides with very small cores. The difficulty is markedly increased in producing waveguides with larger cores, because if the core is larger, just like you need for multi-mode transmission, then the difference between the N1 minus N2 must be extremely small. Okay? As an example, if the optical waveguide is to have a small core, that is a core diameter of approximately 1 micron, the required difference in the two indices of refraction will be of the order of 10 to the power minus 2 in the second decimal place. And if the optical waveguide is to have a larger core, that is a core diameter of approximately 1 millimeter, the required difference in the two indices of refraction would be even smaller, that is on the order of 10 to the power minus 4. That is the kind of difference between N1 minus N2 that you will have to have reproducibly if you are going to have a core diameter of even 1 millimeter. The difficulty of very accurately controlling the diameter of the core, the index of refraction of the core, and the index of refraction of the cladding layer has in the past made the production of optical waveguides very slow and expensive. Okay, so that's really what it is. So their problem was defined, and not only defined in a qualitative way, but they actually had some numbers. They knew what kind of thicknesses of core, what kind of refractive index difference between the core and the cladding they will have to achieve. And these were all things they felt more comfortable with. They said, yeah, I mean, these are still, within our domain. Okay. Any questions? Okay.
No, sir.
So last time I was telling you about fiber optics, okay, and told you also how Corning actually got into it and what was the underlying science which they basically tried to seize upon and then see if they can come up with a product. I mean, so it was definitely based on a scientific understanding of what are the requirements. Okay. Now, what did we say? That two critical things. One was the diameter, the core diameter, the cladding to core ratio, okay, and also the refractive index differences, between the core and the cladding, and that the smaller we make the core, you have a little bit more of latitude in terms of the difference in the refractive index. But if the core is quite large, in diameter, then of course the differences in the refractive index between the core and the cladding have to be will be much narrower, and basically so that we get a value of R which is less than the specified value. Okay? So the question is that how would you consider making these kinds of glasses with different refractive index. Just think about it. I mean, what would you do to change the refractive index? What can you possibly do?
We can put an additive.
Very good. Okay. You can put an additive. Okay. Good. And so we'll put that one can put an additive to alter the refractive index. Okay. So that's good. And that's precisely what you see in this plot. What you see is that suppose I take silica, pure silica, which is quartz, and then I add different types of additives into it. Okay, germanium, phosphorus, aluminium, titanium. Okay, all of them actually raise the refractive index. Okay? So there is a knowledge that had existed in how to really change the refractive index of glass, and also how you change it as a function of the concentration, not just the type of element, but also its concentration. The only exception in this plot is fluorine, which actually tends to lower the refractive index. Okay? So that's also very interesting. I mean that I haven't seen. You'll see when we are talking about plastics that there will be a role of fluorine in that. But generally, I mean, this is what it is. Okay. Now, let me ask you the question. How would you actually incorporate an additive into quartz? What would you do? And it has to be uniform, right?
So, sir, we'll replace one of the silica with aluminum or germanium as it is done in doping also.
Right. No, yeah, that's fine. But I'm just asking. In fact, I hope you can see the relationship between the work of Chapin and all on solar cells and this, where actually, you saw how they were able to diffuse boron into an N-type semiconductor. And first, they created the depletion layer, and over that they could make a very thin layer of the p-type semiconductor. Okay, so that is there, but I'm like in that particular case, they worked out a way of diffusing boron into silicon. In fact, that's another similarity, that in both cases, we are talking about silicon. One is of course elemental silicon, and this is silica. But it's interesting, that both fiber optics and this have silicon as the base element. Okay, I mean it's got nothing to do with anything, but it's interesting to find these analogies. Okay, but I'm just asking you: is there anything? And you have to start looking at precursors. Are there any precursors of things like silica and titanium dioxide, etc., which you might be able to use for a more
Colored
uniform.
glass.
Yeah.
Colored glass.
No, colored. I'm not talking about colored glass. Is not the issue. I'm asking how you will incorporate, like let's say titanium, because titanium seems to have the highest change in the refractive index. So I can put in relatively small amounts, okay, and get a change in the refractive index. Okay, so I'm asking you that how would I incorporate it into glass? Is there any precursor which you can think of, which will allow you to do that? Okay, never mind. We will go on, and then it will become clear to you. Okay. Now, firstly, let me tell you that Corning are not the inventors of fiber optic. Okay? The concept, as you saw, was mooted by Kapany and Hopkins. Okay, and there were many people, including Pilkington Glass and others, who were already making fiber optics. So it's not as if it was not there. But the thing is that there were certain difficulties in getting a good product, which I think Corning appreciated more than others. And even if others had appreciated it, Corning was able to come up with a solution how to actually solve that problem. So, but let us look at the prior art, and this is very important. First, you must always see the prior art, what is known. Then only comes improvements. Okay, so a present method of producing an optical fiber is to insert a rod of glass possessing the desired core characteristics into a tube of glass possessing the desired cladding characteristics. So you're just inserting one glass into a tube. Okay, so out of this, which one will have the higher refractive index?
The core, the rod.
Yeah, the core will have the higher refractive index. So obviously, whatever you are inserting must be having that kind of a property. The temperature of this combination is then raised until the viscosity of the materials is low enough for drawing. So it becomes softened. The glass, and then you can draw just like glass blowers do. I mean that's effectively how they make different types of shapes and sizes of glass objects. Okay, the combination is then drawn until the tube collapses around and fuses to the inside rod. Okay, so we have taken a tube, okay, into which we put the rod. So the tube is basically getting softened and collapsing into the rod. Okay, so that's what is happening. This resulting combination rod is then further drawn until its cross-sectional area is decreased to the desired dimension. During the drawing process, the rod and tube are normally fed at different speeds to produce a fiber with the desired core to cladding diameter ratio. So you can pull the rod and the cladding, the tube and the rod at different rates. Okay, so you can alter the ratio between the cladding and the core. Okay. This method is normally used to produce glass optical fibers having a large core and a thin outside cladding. Okay, so it is not to make the single mode kind of product. It is relatively a large core with a thin cladding. As an example, the total diameter to core diameter ratio of such a fiber might be 8:7. Okay. So it's quite different from when I've got a very thin core, and I could be talking about ratios of 100:1. Attempts to produce optical waveguides with a very small core diameter and a very thick cladding, that is a total diameter to core diameter ratio on the order of 100:1, by this method have been unsatisfactory because of the extreme difficulty in maintaining the core and cladding dimensions. An additional problem is often caused by numerous tiny air bubbles and foreign particles being trapped at the core and cladding interface. These air bubbles and foreign particles are a source of light scattering centers. Okay? So you can imagine, I mean, if the light is going to scatter, then I'm going to have tremendous attenuation of the light. So that is not going to be useful. In addition, the core and cladding materials of any waveguide must be selected so that there is only a very small yet precise difference between the two indices of refraction. So you have to have that kind of glass tube and rod available with this kind of a tremendously well controlled refractive index. Okay. glass tubes and glass rods which have small yet precise differences in their indices of refraction are not readily available. So that was a problem. And yet we know that it is the single mode with a very tiny core and with a fairly large cladding diameter. That is the one which was required for communication, long distance communication. Okay, so it was a very important problem that if you wanted to extend optical fiber into the area of communication, then this problem will have to be solved. Variations in core diameter or in either index of refraction will affect the transmission characteristic of a waveguide. Okay, so that's the prior art. When they got into this, probably sometime in the late 60s, Corning. Now, so now they're describing what exactly they did. Okay? Broadly, according to this invention, an optical waveguide is produced by applying a film of material on the inside wall of a glass tube. So they didn't really put a rod inside the tube. Okay, they just applied a film over the in the underside of the glass tube, in the inside area. This film of material may be a glass possessing the optical and physical qualities desired of the waveguide core, a doping material that will diffuse into the inside surface of the glass tube, thus forming a film of a glass on the inside tube wall having optical and physical qualities desired of the waveguide core. So that would be very, very similar to the kind of approach that was taken by Bell Labs, while making the silicon solar cell. So they're talking about, because I just need a very thin film, because finally it will become the core with a very small diameter. So they're saying that from the inside, I can try and diffuse some dopant into that glass. So the characteristics of the inner tubing will be different from the outer tubing. Okay, so that is one. Okay, or a doped glass, the dopants of which will partially diffuse into the inside surface of the glass tube, resulting in a combination film of applied doped glass and doped glass formed by diffusion. So what they're saying is, I might actually have a glass which has incomplete level of doping, and then I complete the rest of the process, through the diffusion of the dopant into the glass. Okay, this composite glass structure is then heated until the structure reaches a temperature at which the materials have low enough viscosity for drawing. The composite structure is then drawn to reduce the diameter thereof until the film of core glass is collapsed. Okay, so finally you see the rod which I am producing, the core, there's no hollow there. It's a solid glass. Okay, so basically what will have to happen is that as I'm drawing, the inner film will collapse into a rod and the cladding will be over that rod. The composite structure is then drawn to reduce the diameter thereof until the film of core glass is collapsed. That is, it seals the longitudinal hole to form a rod surrounded by cladding material. Thereafter, continued drawing of such a composite rod further reduces the diameter thereof to form a glass optical fiber which possesses the characteristics of an effective optical waveguide. So first you basically have to create an inner film so that there is a refractive index differential. Then you start softening the material and drawing, letting the film collapse into a rod. Okay, and thereafter you keep drawing. Okay, to get the whatever is the final diameter of the optical fiber, that you want. So you can also imagine that depending on the thickness of the film which you are using, okay, I can have different core diameters, okay, because it is that film which is collapsing into a rod. So the thicker I make the film, the thicker will be my rod. The thinner I make the film, the thinner will be the rod. Okay. Is that clear to everyone? All understood?
Yes, sir.
Diameter thereof to form a glass optical fiber which possesses the characteristics of an effective optical guide. That is, it transmits what is meant by effective. That is, it transmits pre-selected modes of light without excessive attenuation. Okay. So in this, once I made a film on the inside and then I'm stretching it, okay, I actually do not really have that kind of a bubble formation, which was formed when I've inserted a rod into a tube. Okay. And so there is not much of an attenuation. It is not subject to crosstalk by adjacent optical waveguides, which means that the total internal reflection or the transmission within the core, is absolutely perfect, almost perfect, so that there's no interference of signals from one fiber to the other, and it does not cause excessive dispersion in the transmitted light. So these are really the what they were looking for and what they were able to achieve. So you can look at what they are basically saying. So I put a film, okay, on the inside, all right, and as I'm drawing, you can see that this film is collapsing here into the core. Okay, this is what I've got. And how am I doing this? I'm basically stretching. So I've got a hollow inside initially, okay, and then I've started to pull, okay? And finally these things from both sides will collapse, and it will form the inside core. Okay, that's what you will have. So I'll have a core, and then over that I'll have this cladding. So that's effectively it. And they've said, they're giving a specific example so that you can get some idea of the numbers. A specific example of a waveguide produced by the practice of this invention follows. A 1.5 to 2 micron film of fused silica doped with titanium oxide was bonded to the inside wall of a 3/4 inch outside diameter, 1/4 inch inside diameter, substantially pure fused silica tube by the method described in said co-pending Keck-Schulze application. The deposited doped fused silica essentially consisted of 94.75% fused silica and 5.25% titanium oxide. And so you can actually go back to this and you'll know what is the difference in the refractive index which they would have achieved between the between the core and the cladding. The composite structure was then heated in substantially an oxygen atmosphere until it reached a temperature at which the materials had low enough viscosity for drawing. And what is that? It's about 1900 degrees centigrade. So you need special furnaces to reach these kinds of temperatures, like the induction furnaces and those kinds of furnaces. The composite structure was then drawn to reduce the diameter thereof until the film of titanium oxide doped fused silica was collapsed. That is, it sealed the longitudinal hole to form a solid core surrounded by pure fused silica. The resulting composite rod was then further drawn to reduce the diameter thereof to a final diameter of approximately 100 microns. So you can see that we are starting with something like a 3/4 inch tube, and the final, when I have made the fiber, okay, it is achieving a overall dimension outer OD of about 100 microns. So I mean, you can actually work out for yourself that even if I take a tiny glass piece, maybe a foot long, okay, and I can actually pull on it and make these fibers and those I can generate kilometers of fiber from that. Okay. The core of the optical waveguide was measured at approximately 3 microns in diameter. So they are talking about cladding to core ratio, roughly about not 100:1, but closer to 35:1. The core index of refraction was approximately 1.466, while the cladding had an index of refraction of approximately 1.4584. So you can see how tiny the difference is. I mean, if you were to look at the first decimal place, you would not see any difference between the two. After the fiber was drawn, it was heat treated at 800 degrees centigrade in an oxygen atmosphere for approximately 3 hours. Okay. Now the question is that how exactly they're saying that you dope it with this and all. Okay, but let us try and see. Okay, what exactly they are doing. Now this is actually an interesting approach, and what all of you should look at is that when you have this kind of a problem, okay, and I asked you, what is the precursor? Now, obviously, we know that if I take volatile things, okay, then they will mix uniformly, right? If I take two gases and I mix them, then I'll get a mixing of those gases, So what they realized was that silicon tetrachloride. What is silicon tetrachloride? What is the physical form of silicon tetrachloride? Does anyone know? And titanium tetrachloride?
Liquid.
Liquid. And it's a very volatile liquid. Okay, both of them. And that's how actually the pure silicon is made, from silicon tetrachloride. Okay? So, I mean, it's interesting. And I hope you can understand the crucial intermediates, and which has a bearing on fiber optics as well as on solar cells, that they all actually start with something like silicon tetrachloride. Okay? And so what they were doing was that they were making a mixture of silicon tetrachloride and titanium tetrachloride, things like that. Okay, and which was taken in a way, all right, that that the two will basically deposit, okay, and it will deposit in a very uniform way. Okay, so so suppose I've got the inside tube, or it could be on the underside of the glass or on the outer side of the glass, depending on how exactly you're doing your work. So I'll talk about the second way in which they approach this problem. The first one, you saw how exactly they achieved their product. So that film which I put in the inside of the tube could be actually made by this kind of a method. And obviously, when I've got titanium tetrachloride, the refractive index will be higher. Now, the second is that they also said that what if I want to make an optical fiber which has got a large core, okay, and a thin cladding. So I'm talking about an overall dimension, something like 10:1 or thereabouts, or maybe not 10:1, 10:9, 100:95, that kind of an overall diameter to the core diameter. Okay, so there what they did was something again, and this is again, once I've devised a platform, and for them the platform was to be able to take volatile intermediates, mix them, and be able to convert it into a film. Okay, so now I can play around. So let us look at how exactly they did the other one with a relatively thick core, okay, and relatively thin cladding. Okay. Then it says the total diameter to core diameter ratio for multi-mode optical waveguides is preferably in the range of 1001:1000 to 10:1. So, I mean, this is of course the typical patent language, and they will confuse you so that you don't exactly know what they've done in many of these cases. Okay, just bear that in mind also. Okay, and for a single mode waveguide in the range of 10:1 to 1000:1. Okay? So 1001:1000, and this is 1000:1. So you can see, what a drastic difference in the cladding to core thicknesses. Okay? Now, although ratios outside of these ranges would also be operable. This is the patent language which you have to understand. And if you are writing your patent, you have to write it so that you are covering yourself well enough. Okay? Then it says how exactly they made this multimode. A specific example of a multimode waveguide produced by the method of the present invention is as follows. A starting material of fused quartz, approximately 1/8 inch in diameter and about 10 inches long. Okay? So you can see your starting object, the glass piece is nothing. I mean, it's just like a regular glass piece. This is not something very unusual. And so 1/8 inch in diameter and about 10 inches long, and a starting material of fused quartz, okay, approximately this is sealed to a suitable handle. Okay, so they have just taken a rod. They have not taken a tube in this case. It's just a rod of glass. A liquid mixture containing 30.4% by weight TiCl4 and 69.6% by weight SiCl4 is heated to 35 degrees centigrade. Okay, that's what they're doing. Dry oxygen is bubbled through the liquid mixture, and SiCl4 and TiCl4 vapors are picked up by the oxygen. Okay, so basically what is happening is that SiCl4 will get converted into SiO2, and TiCl4 will get converted into TiO2. This vapor containing oxygen is then passed through a gas oxygen flame where the vapors hydrolyze to form a steady stream of approximately 0.1 micron sphere-like particles having a composition of 2.5% by weight TiO2 and 97.5% by weight SiO2. Now, this is very interesting. It's not clear to me why, if they start with a percentage which is 30.4% and 69.6%, of TiCl4 and SiCl4, how they are actually achieving, this kind of a ratio.
So when we are bubbling oxygen through that liquid,
They are, as you said, they're doing the volatilization by bubbling oxygen through the liquid.
so maybe that is the reason that we are getting this 2.5 and 97.5. Like oxygen is that mass transfer rate is in favor of silicon chloride.
Very interesting. You could be right. Okay, let us see what are the boiling points. Boiling point 136.4. Okay, TiCl4. Okay, so let us see what is the other one. Yes, you're right. Okay, this is 57.65. Okay, that's brilliant. Okay, let's just put this over here. Today, the ratio of Si to Ti in gas phase varies from the ratio in the liquid mixture taken because of the difference in their boiling points for silicon tetrachloride. Boiling point is, how much was it?
57.
57.65. Huh? 57.65 C. And for titanium tetrachloride,
136.4.
it was 136.4.
4.
This is marvelous. Very, very nice. Okay. You found the reason. Why don't you do that? They're initially getting not a uniform film. Okay, they're getting islands, small, tiny pieces of glass, okay, glass spheres. A stream of approximately 0.1 micron sphere-like particles having a composition of 2.5% by weight TiO2 and 97.5% by weight SiO2. The stream is directed to the starting member. Okay, so you're forming what? Effectively like a suit. That's what you're forming. It's just like a suit, just like we have kajal, in a very colloidal form. Okay, so that they were putting on the outer rod, this particular rod. Okay, so the stream is directed to the starting member, and a soot layer of these particles is built up to about 1.5 inches in diameter. So from something like 1/8 inch, which is the initial thickness of the rod, they're building up the thickness to about 1.5 inches in diameter. Okay, so a huge amount of soot is actually being applied. This layer of soot is then sintered in an induction furnace having an oxygen atmosphere at about 1500 degree C. So that's what they're doing. So they're sintering, and all of these islands of glass, that soot, is collapsing into a coherent kind of a piece of glass or a film of glass. Thereafter, the outside of the sintered core glass is mechanically polished to an RMS finish of approximately 5 microinches. So whatever, after I've done the sintering, etc., they're polishing that outside of the tube, and just getting a very mechanically smooth kind of a surface. Now, so this is, and we'll see, it will be interesting. The fused quartz starting member is then ground out by means of a diamond reamer. So, what they're saying is that the initial material, this rod which they put, now is being drilled out. And not only is it being drilled out to the extent that I had the initial diameter, which is 1/8 inch, but obviously they are drilling out quite a bit of it, so that even some of the soot which became a glass, a film of glass, even that is being drilled out. Okay, so because that because the final diameter which they're achieving is 5/8 inch, whereas they started with 1.5 inches, so quite a bit, of that stuff has been drilled out. The tubular member so formed is rinsed in about a 50% hydrochloric acid solution, flame polished and washed again in said acid solution to provide a clean tubular member having approximately 5/8 inch outer diameter. That's what they're doing, So that's what they've got, and they've got rid of the initial rod, over which they made their film. Okay. A second coating of 100. So now this actually, whatever they applied first, will become the core. You know. Now they have to put the cladding. A second coating of 100% SiO2 is applied over the tubular member by the same flame hydrolysis method described above, except that the liquid mixture does not contain TiCl4, shall get pure silica. The SiO2 soot is applied until an outside diameter of approximately 1.5 inches is obtained. You know? So that's what you have. Okay? This structure is then placed in an induction furnace wherein the SiO2 soot is sintered and the resulting composite structure drawn in an oxygen atmosphere at about 2000 degrees C. So they're repeating the process, but now they have actually applied two films over a glass rod which has been removed. Okay, the first film becoming the core and the second film becoming the cladding. As the structure is drawn, it decreases in diameter and the central hole collapses. Drawing is continued until the final desired waveguide dimensions are obtained. Typical final waveguide dimensions may be a core diameter of 120 micron and a cladding diameter of approximately 40 micron. You know? So you've got some idea, you know, of what they are basically talking about. You can see, okay, so this is my first film which I put over the rod, okay, and this is the rod which will finally be ground out. So it's being taken out, okay, and then I've applied my second film, okay, which will become my cladding. Okay? And then when I'm grinding out this rod and then I'm collapsing these things, okay, I will ultimately end up, okay, with this is the core, which will become the core, okay, and this will become the cladding. All clear?
We do the production process in the other way. Like here, we are increasing the refractive index of the core by doping it with titanium. But
Yeah.
if we take the core as the pure glass and we lower the refractive index of the cladding using fluorine, so
Yeah, I
can that
think,
be done?
you know, that's why I showed you that plot.
Yes.
It's very interesting that, of course, I mean, why would you want to do that? You see, because remember, fluorine is not so easy to handle. Okay? Fluorine compared to TiCl4 would be more difficult to handle. You know, but in principle, what you're saying is correct. What I think one will have to look at is the relative stabilities of these glasses, you know. But you are absolutely right. I mean, there's no reason, okay, why you cannot reduce the. So you take pure SiCl4 and then you're saying fluorine doped silica, right?
Yes, sir, as the cladding.
Absolutely. I think that uh, there's no reason. Okay. I'll just put that also.
Sir, I can think of a reason like,
Tell me.
sir, so because the optical fiber that we are trying to make, it has a thicker cladding and the core is very thin.
Yeah.
So it makes sense to put the additives in such a way that we use the least amount of them, right? The dopants in such a way.
Yeah.
So, so if what Harsh is saying, so the cladding should have lower refractive index, then we'll need to have a lot of fluorine to make
Yeah.
up for
Right.
the thicker
The
cladding.
fluorine consumption would be higher. You know.
But
That's
in
true.
this
But
way, we
I
are just
think, well, let us put this down. You know, student, uh, why can't we take a core of pure silica and cladding which has a lower refractive index to fluorine incorporation. Okay. See what may be the pros and cons. Okay. Right. And I think the stability, performance, cost, okay, process difficulties, etc. Clear?
Yes, sir.
Okay. Yeah, I can, but what I really like is that all of you have begun thinking, and this is exactly what is required. I mean, the purpose of this course is not to just tell you how great some past inventions were, but to appreciate that knowledge is never at a standstill, and it will move on. And somebody someday will come up with something different. And absolutely, this question needs to be asked, And in fact, the reason why I showed you this, as I told you, is because of this, that, I was intrigued by the fact that fluorine actually reduces this. And you'll see the role of fluorine, in some fibers, in my
So,
next few slides. Okay.
so one more, like
Yeah.
in the graph, it is the dopant concentration is only till 2%. Like for others, it can be increased like 12-14% also is there.
Yes.
So so maybe
No, but then see, I don't want to apply, this kind of a refractive index change with 2% is sufficient. No, okay, it may be enough. And if I can use less, then I'll use less. Conceptually, actually, it is possible, in terms of the refractive index, but have a look at what could be the difficulties. By the way, this is what is meant by brainstorming. So somebody comes up with an idea, and then other people start looking at it critically and seeing whether this idea can bear fruition or not. Okay, but never shoot down the idea. Keep the idea there and then see if there is some way of circumventing the problem. But most important is you should ask yourself, what would be a tangible gain? Would I gain anything, or would I do it simply because it's a variant? Okay, that's the issue. So commercially, I have to ask myself, why would I do it in the first place? Even if, let's say, scientifically, technically, it's possible to do. Do I see any advantage of doing it? So those are the kinds of things that you should ask yourself. Okay. Now, this is also very interesting, and a very different way, okay, of making the optical fibers. Where what is done is you actually take molten SiO2, okay, and you take maybe an SiO2 which has some TiO2 incorporated in it by those previous methods, okay, and you put this, whatever will be the core, it will be at the bottom, and whatever will become the cladding will float over it. Now, this is possible, okay, because what would you expect I think that the density of titanium oxide, will naturally be more than that of silicon dioxide, right? What do you think? Let's see. Density of silica, 2.65. 4.23. We can put this down. Okay. You may say, but why should the stuff which is going to become the core, why should it be at the bottom? It will be, since core has titanium dioxide and the density of TiO2 is much higher than that of SiO2. The molten core composition would be at the bottom. Okay, is that clear to everyone?
Yes, sir.
And what were the values? Let's just one was 2.65. What was the other one?
4.23.
Something. 4.23 and 2.65. 4.23 gram per ml. Also, you see, because molten things would still be very, very viscous, two things will happen. You know, your convective mixing will not be there, because I'm floating the thing, which is, I mean, what is in the top is really something which is less dense, and therefore it will remain there. You know, it won't have any tendency to sink. Okay, so so basically, what they're doing is they're taking these molten mixtures, okay, of TiO2 and SiO2, and then over it, they're taking a molten silica, which will have a lower density, and therefore it will float on top. And now I'm just inserting a glass, okay, or metal or something, and I'm just pulling, you know. So when I'm pulling, this will become my core and this will become my cladding. Is that clear?
Yes, sir.
But
Okay.
how can you pull it? Like, I don't understand.
Why am I able to pull? Because firstly, it is very viscous. You know? So initially, as I'm beginning to pull, okay, once the temperature goes below the that of the melting temperature of glass, it will start solidifying, right? So I can just keep pulling the whole thing, and what I'll be pulling out will be a solid. As I told you, and things could change. Okay, that some of the requirement of optical fiber for communication in the future could actually be carried out with these multiple satellites which are connected. And so I was actually just looking at the Starlink of Tesla's program, and what they say is, by being closer to our planet and networking together, Starlink satellites are meant to carry large amounts of information rapidly to any point on Earth, even over the oceans and in extremely hard to reach places where fiber optic cables would be expensive to lay down. You know? So that 9,000 kilometer long cable connecting Japan and the US, is it required? And it is likely that in certain areas you will find that the optical fibers will get dislodged, but not in all areas, because the fidelity of information, the avoidance of crosstalk, etc., is likely to be better when you have these kinds of fiber optics. Okay. Now, one more which I was looking at, and for those who have an interest in polymers, you might find this interesting, whereas glass might not interest you. Okay, that there are actually optical fibers today, which you can make, which are completely of plastic, both the core and the cladding. Okay? And I was looking, and look at this. I mean, this is from the 80s, 86, Mitsubishi company. Okay? Plastic cladding composition for plastic core optical fiber and plastic core optical fiber prepared therefrom. Okay? I mean, it's really very interesting, and you can start looking at what are the kinds of polymers and their refractive index properties, how you will actually make these kinds of things. But there are huge advantages. You know, a plastic fiber is obviously not going to be as brittle as that, and even though you are putting a lot of layers of protection and changing the bending angle so that the breaking it doesn't break, but still, I mean, this kind of a plastic fibers may be of interest, especially for short distance applications. So if I were looking at it in the human body, for example, I mean, that optical fiber based on plastic would be fine. And in fact, when I was looking at it, it says something interesting. One of their negatives is that these plastics can operate over a very narrow wavelength, 400 to 700 nanometer, which is the visible range. But that's exactly what I want for the human body. I don't want to have ultraviolet radiation going into it. So that's what they say, and they also say that also, although a narrow spectrum of transmitted light is listed as a con, means a negative attribute, this is actually a pro for medical instruments. Plastic fiber optics are often used to illuminate the inside of a body during surgery due to the fact that certain wavelengths outside of visible light are harmful and cannot be present. So that's what is being done to actually illuminate the body and let the surgeon see what they're doing. Okay? And this is another very important area, which is the use of optical fiber for applications of light. Okay? Not for communication, but for light. Like, for example, if I want to bring the sunlight into my room, okay, without the heat, okay, one of the ways in which I can do it is through use of fiber optic cables, and I concentrate the light outside and let it be transmitted through these kinds of fibers. Okay, so illumination, backlighting, trim lighting, street lighting. Okay, these are areas where these plastic optical fibers are becoming important. Okay, so I'll send you this patent. Have a look at it, especially those who are into polymer. I find this absolutely fascinating. That there are so many other applications which you can think of.